Is gravity bringing you down? The purpose: to determine how the pull of gravity on different planets and Earth's moon impacts weight and jump distance. Background: gravity is the force that attracts a body towards the center of the Earth or toward any other physical body having mass. The more mass a planet has, the more gravity the planet has. So stop here and write down what planets have least gravitational pull and what have more gravitational pull. So if you put planets over here like Saturn and Jupiter, because they're larger, yeah, they have more gravitational pull. Earth and Mars, they have least gravitational pull. In this lab, you'll explore the impact of different gravitational strengths on both weight and jump distance. Draw arrows in these two pictures to show the direction of the force of gravity in each of the following diagrams. So here we have weight is pushing down on you. Here, gravity is pushing you and pushing you down this way. Part 1. How much would you weigh on different planets and the moon? Recall from the background section that planets with more mass have more gravity. For this lab, we will be considering the gravity on other planets in relation to Earth's gravity, our normal. Therefore, a planet with gravity greater than the gravity on Earth will be considered to have more than 100% of Earth's gravity. And a planet with less gravity than Earth will be considered to have less than 100% of Earth's gravity. So you can choose to record your weight here or the weight of an athlete from a class list. So you can have Chara from the Bruins at 296 pounds, or you can use your own weight. Below is a table that shows each planet, moon, and its percentage of Earth's gravity. The percentages are written as decimals to help with your calculations. Multiply the weight from above by each decimal to determine the weight for that planet. So for example, if I was doing 100, and if my weight was 110 pounds, on the moon, I would do 110 pounds times 1700. I would like you to be doing this on graph paper. Do all the calculations out, and then put your weight in pounds here. So I would do this out on paper, 110 times 1700 gets me 18 pounds and 18.7 pounds. As I keep going, you're going to do that for every single planet. Part 2, how far can you jump on other planets or the moon? First, you'll need to find out how far you can jump on the Earth. Stand with your toes at the edge of the floor tile and jump as far as you can. No running starts, please. Have your partner note where your heel strikes on the ground. So if you're doing this at home, you might need some help from a family member. Measure the distance from the edge of the tiles in your heel strike in centimeters. So you're going heel to heel. So you'll need some sort of measuring device in centimeters, so a tape measure. You're going to jump 3 times and measure from heel to heel. So write your jumps here, here, and here. To find your average jump distance, you're going to add all 3 together and then divide by 3. So let's say I jumped 24 centimeters, 31 centimeters, and 30 centimeters. To find your average jump distance, we do 24 plus 31 plus 30. We get 85. And then we need to divide that by 3. Would be 28.33333 centimeters repeating. We'll call it 28 3/10. To find how far you would jump, divide your average jump distance by the percent of Earth's gravity. So we do 28.3 divided by 1700. And I get 166.470588. We're going to round to the nearest tenth. So I'm going to do 166.5 centimeters. And you would complete that for all of these. You can be using graph paper. In this section, we're going to answer all of the questions. On which planet, moon did you weigh the most, the least? Which planet, moon can you jump the farthest, the shortest? For which two locations was your weight the same? Why does this make sense? On which of the two locations was your jump length the same? Why does this make sense? Take that out. Create a scatter plot to analyze how the pull of gravity on different planets and Earth's moon impacts weight and jump distance. First, complete the table below. So we do our weight in pounds, 110. Your jump distance, let's go back to part 1 for the jump distance. Part 2 is jump distance. On the moon, 166.5. On the moon, our weight is 110 divided times 0.17. Gave us 18.7 pounds. Ordered pair, this is what we'll be graphing, would be 18.7 and 166.5. And you would do that for every single one. So this part here comes from part 1's graph. This one comes from part 2's graph. And then you put the ordered pair here. On a sheet of graph paper, plot your ordered pairs from above. Label each point with the planet it represents and the gravity decimal. Also be sure to include a title and axis labels. Questions about your graph. What do you notice about your graph? Answer the central question of the lab. How does the pull of gravity impact weight and jump distance? Why does this make sense? Reference the diagrams you labeled at the beginning. Apply. Imagine that a new planet is discovered whose mass falls between that of Mercury and Venus. Put a star on your graph where you would expect its ordered pair for weight and jump distance to fall. Explain why you placed your point at where you did. For the graphing portion, we want to round all the data to the nearest whole number. So this one would be 19, and this one would be 167. When you plot this, you get to pick 3 to plot. You only have to plot 3 things on your graph and then turn it in.